you see that, of MadeUp or Startup, where, as you recall, we trained this fancy model, this LSTM model with a few layers, to generate startup names based on a big list of startup names that we have. And it did a perfectly fine job of doing that, but what we need to do is take this model and futz around with it a little bit so that we can get out on demand one startup name, one startup name, one startup name, ideally with essentially zero prompting to just generate those for us. That's really what we need to do. We need a system that does that, because what we're eventually going to do is have a system that generates those startup names and then feeds those into a discriminator or judge? I forget the exact term. I think a discriminator, or a critic. Critic is the right word, excuse me. It will take those, read those in a character at a time, and at the end try to predict, was this a real name or was it a fake name? Real or fake, real or fake, real or fake. And that's how they each get the reward. If the critic is correct, it gets a reward. If the model fooled the critic, then the model gets a reward. And probably the model, I'm going to keep that relatively the same, relatively speaking. Except we're going to, of course, we're going to have to change this up a little bit in order to get the correct kind of data that we actually want as our output. Like here, we're outputting a character at a time based on whatever our previous input was. But really, we need to output a sequence until we get the end name, the end startup name character, which is, of course, just a new line. Let's just read in some stuff, just so we got it. Let's rebuild our data set. Always good to rebuild our data set. We're not going to retrain the model, though, because we've already done that. If I say we, I mean I did that like a year and a half ago, and I haven't touched it since then. Oh, it was longer than that. It was like 2 years ago. Yes, just about 2 years ago. Maybe 2.5. It was a while ago that I worked on this. But it made for a really good trivia night, so I highly recommend it. Yep, those are all those characters from collections. Run all this stuff, reparse our data out, do all that stuff. Okay, I don't need to actually train the model. No training. But we are going to load weights of the model. Okay, we have a model with these weights. What I need, though, is a model that either in Keras or TensorFlow or whatever produces all these things, because what we're going to end up doing is generating these, and then one name that gets generated goes to the critic, and then the critic takes in that name and tries to assess it. I guess one thing we could do is is just work on the critic model, actually, and then work on connecting those things. But I want to do a quick internet search and say something like name generator, I don't know, GAN, not gangster. We'll say like machine. We'll throw machine learning on there. Generating letters, that's not exactly what I want. That's close. Beginner's guide, the generative. We'll see if this is what we want. Variation law of encoders is something totally different. How old is this? Okay, just a year and a half. Just want to see the outputs. I don't just want to see the output, but training set, generator. Oh, you feed it random noise. That's a good idea. Feed it some random garbage. See what you get. Interesting idea. Interesting idea. And then your discriminator gets it and has to say yes, no. Okay, cool. So I haven't worked with GANs a whole lot. So that's why there's going to be a lot of me figuring this out live on the show. Which you might, if you've been watching the show for a while, you know, like, that's how I figured out convolutional neural networks. But it makes a great way to understand what the heck is it that you're doing. Here they're doing this image-based thing, which is not exactly what we're doing. Here it's actually a little bit, not easier, but more straightforward as far as what's going on. You're generating an object of fixed shape. What I want is, like, sequence generator. Right, I could fix the shape and say, like, well, it can only be yay long. Okay, that's fine. Sequence generative adversarial, and that's with policy. Syntax aware sequence generation, sequence scan. Sequence generative adversarial network policy. We'll take a look at this paper. New way of training these things arrive. Generative adversarial nets, discriminated model. Generating sequences of discrete tokens. Yes, that is our problem. Discrete tokens from the generative model make it difficult to pass the gradient. Yes, this is going to be the hard problem. You're generating, 8 or 10 or however many outputs of your model, but you only get information at the very end. So I was like, well, how do we update the model to do that? Scheduled model can only assess a complete sequence, while for a partially generated sequence, it is non-trivial to balance its current score and the future one once the entire sequence has been generated. Sure. You propose a sequence generation framework to solve these problems, and this is from 2016. This has been out for a while. Modeling data generators, a stochastic policy in reinforcement learning, sequencing and bypasses, blah, blah, blah. So it's a reinforcement learning thing, which is, of course, what it is. It's passed back to intermediate state action using Monte Carlo. Hang on. Comes from the GAN discriminator, judged on a complete sequence, passed back to the intermediate state action steps, so every step gets some information. Extensive experiments on synthetic in real world demonstrate significant improvements over strong results. Intermediate state using Monte Carlo search, also known as try a bunch of things. I will dig into look at this a little more closely. I don't want to spend like this show just reading the paper. That's kind of dull for you guys. So I want to find some specific information. You got your true data, you got your generated data. G, you got some state, the next action, Monte Carlo search, and you get the reward. So like you just try out a bunch of different things within the network. Maybe if I just search CGAN. Do I get anything other than this paper? Okay, we get a GitHub repo. That's a start. Using TensorFlow 1.0. Python 2.7. So sad. But this is from several years ago, so that's not surprising. They do have a Medium post, which might have some more information. Sequence generation. Blah, blah, blah. These are supposedly AI-generated pictures, I imagine, which are terrifying. Oh, someone's using Matplotlib. I dig it. Gradient of the loss from D. What we might end up doing is not super good. The goal is to maximize J. The objective to generate a model, generate a sequence, maximize it. Yeah. You want to fool the output is what it is. Actually, what I really should do is Keras GAN sequence. 1D generative adversarial network. That's probably a good first step. So like this is just how the process works. Like, okay, I need to do thing X. I need to look up some stupid results about how to. So this is just from December. What do you know? And there's going to be terrible pages with lots of pop-up ads. You got to deal with it. Complex type of model. Yada yada yada. One-dimensional function. Yeah. Oh, this is just get a simple, literally 1D function, not a one scale of output. Yeah, that's not quite what we wanted. It's a little too simple. Although that might still have useful terms in terms of how do you make Keras do this. GAN by example with Keras, TensorFlow backend. This towards data science has so many little pages, but the quality is very hit and miss. Start to see reasonable images at about 5. Whoa, what is this? Train auxiliary classifier GAN on the MNIST dataset. What in the nonsense is this? NumPy. You make some CNN model. The generator, which is a model. It takes random garbage input. 3 to 3 to 384, sure. Oh, it takes random dense input. No, input dimension, latent size. I see. And he's got the discriminator, which takes in the actual image input and has to guess true or false. See if this exact same nonsense? Well, this is something else. Hang on. This one. Oh gosh. This is not a Keras thing, is it? Okay, here we go. This is your discriminator, which builds a simple model, sure. Is your discriminator actually, do you have a Keras generator? I don't think you do. Generate fake examples, train discriminator. You are just training a discriminator, aren't you? X. Are you just using NumPy? Define a generator model. Okay. Sure. Now you have your generator. Do all this stuff. Generator plot. Super simple model. And then how are you combining these two things? I don't really care about the latent points nonsense. Generate point of latent space as input. Yeah, that's just random nonsense. Don't care. That's the model. You can generate fake data to your heart's content. In the GAN, you create a model, you do your generator, you do your discriminator, and then you just do that. Wow. Okay. That seems odd. I guess hang on, but the discriminator, you need a bunch of training data that doesn't actually go through that doesn't come from the generator. How do you get that? Or am I misunderstanding what this guy's discriminator works? Dense N outputs, activation linear. No, I think it's just got those output shape 15, output shape 2. That's weird. It's weird to have two outputs when you really just need one probability. That is a bit odd there. And outputs. Unless he's trying to predict one of three classes? I didn't actually see what he was doing here, so that's my own stupid fault. I don't think he is. An XY maybe is what he's predicting? That could be. Yeah, I think that's correct. So those are fake samples. Those aren't on the actual data. Yeah, you just use the generator. Generator feeds right into the discriminator. And it's a sequential model. And you just want to know, did this piece of whatever come from the actual data? But how are you going to feed? Oh, you train the generator separately. This is how you train the generator. Right. The discriminator you train also separately by giving it real data as well. I see. I think, anyway. Because otherwise, they're all false, right? You put in some data to the generator, obviously that's false data. Unless the generator has some... No, there's no, like, probabilistic chance that you use real inputs, and it just passes them through. That would be the alternative. That you always pass in, you seed with some real input. Or there's some probability that you do, but I don't see that happening here, actually. I'm not sure that this is correct. Train GAN. Generate latent points. GAN model the train on batch. Points in latent space. Yeah. Generate a bunch of random points. Who cares? Create inverted labels for the fake samples. Yes, they're all fake. And then generate real samples, generate fake samples. D model is your discriminator model. Right. You train that just on the generated and the fake. And then the whole GAN you train on some generated fake stuff. Okay, I see. So this is, yes, you have to do train the discriminator a little bit, and then train the actual. That's kind of annoying that you have to use it this way, but I don't know if there's a better way to do that. There's this nonsense. But this is all getting away from what I'm really trying to do, which is to generate a sequence. That's really what I want to do, like Keras sequence generation is probably. Keras sequence generation. Text generation, LSTM recurrent networks, yada, yada, yada. I mean, this is the things that I'm doing already, and this is just what happens. You have a bajillion tabs. That's what's going to happen. We'll close off some of those. Blah, 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 blah. This is just a way to read in a bunch of text from Nietzsche. Great. And yeah, I think I've used this exact code right here. It's kind of funny. But this is just generating a character at a time. This is not generating the full sequence. That's what's grinding my gears. We'd have to change this output to be like an n by something if we want the actual sequence output. And then my proper predicted output needs to contain that as well. So why don't we just do that? And then we're going to pick n. You know, that's going to be the easy thing. Pick n. It is what it is. And we just need to futz around with this a little bit. Because you could pick n, you can say, you know what, n equals 16. All my startup names are 16 characters or less. And the way that one has to structure that is that all your little sequences are going to be whatever the things they are, A, B, C, D, E, whatever, and then a bunch of end characters to make up the difference, right? So that becomes whatever your object is. I needed 3 more ends. 1, 2, 3. 3. Right. And then this becomes your sequence that you shove in. And so probably what I would, you think about this here, you get a bunch of characters and you want to learn to generate, yeah, so you could restructure this so it's not an LSTM type of problem. So maybe that's actually the approach we want to take if we're going to do something like this, right? If we're going to do, you know, 16 long. I might actually rather just do 8 long. Where's my startup name list, actually? Data? Those are pretty long, actually. Chars, max length, data. Data split of new lines. Let's see what kind of lengths we got going on here. And I want to list map length and all that. So I want to know how long are all these things. That's a lot of things. So what I want is not by. I want that. But I want. Do I have counter? I might have counter already. Yeah, there we go. That's a lot of things. That's kind of a mess, though. To be honest, I'm really like unupy.hist. Oh, gram. That's really all I want. Right. So some of these are hideously long. Most of these are not too bad. So it looks like the vast majority are less than 0. So this is between 0 and 6, 6 and 12, 12 to 18. And if I set my bins in a particular way, A range, I don't know, up to 32 long, something like that. That's probably fine. Jack that up. What? Somewhat wrong here. That's the list. That's definitely how long everything is. Oh, no. I did this wrong. I just want that. Right. There we go. 4 things were exactly over 32 long or whatever. This just gives you a little bit better breakup. So you can see like how many are 0 long, which shouldn't be any, but apparently is some. You know, 1, 2, 3, 4, 5, 6. And in fact, let's import matplots, lib.pyplots, splt. And in fact, there's a hist command right here, and you can pass in bins the same way. So let's do this, but we'll just say plot.hist. Doink, and you get a nice little diagram like this. It's a little bit easier to interpret. Kind of a typical log normal distribution for how long these names are. Long tails. And of course, there's many that are more as the tails would have continued on. So yeah, 16 would actually capture most of things. 8 would capture like the first half. 16, 32 would capture just about everything. I don't know if I want to have that many outputs though. So this would be foregoing LSTM-ness, which maybe is okay. We can say that's fine. And probably doing a like 1D convolutional thing, which in some sense is very similar actually. I kind of like that. To be honest. That will mean building a new model. But hey, that is perfectly all right. I had this like LSTM model, didn't want to train a new model, but things happen. I do want to think about this, however, though. Data, hang on. Data split of this nonsense, how long is that? We got 26,000 of these guys. So I'm going to call, that's how many we have. I'm going to figure out how much memory we're going to be eating up here. I believe I have 28 characters in my alphabet. Like all the letters, plus a space, plus a new line, which is the end character. So I got that times, if I'm going to have 32 characters I'm making predictions on. You know, that's doing that, and each one of these is occupying, 4 bytes, float 32s. We're using this much memory. Okay, so that's less than 100 megs. That's actually much better than I thought. A megabyte being about 1,000,000 bytes. It's like 2 to the 20 bytes, really, but yeah, about 1,000,000. So 93 million I can tolerate. 100 megabytes there. That's not too shabby. So it's really about how big is the model. Because we're not going to get burned on this. Because from now we're just going to be predicting what is the... Give me the output. Give me the output. Give me the output. What we'll need to put in, though... But we're no longer generating... Yeah, we'll no longer be generating these from partial sequences. So we'll save a lot of memory that right now where I have a lot of things that are like HA, and then the next character is S, AS, and the next character is H, SH, and the next character is F, and all that other nonsense. Let us make a new model. We'll call this convgen.py. What we're going to do, we're going to grab all this stuff. Yeah, we'll parse our data pretty much the same way here. Pretty much the same way. Really, I should just, save the data at some point. In fact, let me grab all this nonsense, too. Okay, parse the data the same way, that's all fine, well and good. Build a model. We're going to build a new model. Build a model, 1D convolution. 1D convolution, create 32. 32 long output. Prob. Vector. There we go. The question is, what do you want to have as input? Is really the answer. So I don't need these LSTM things anymore. Those are all gone. Poof. Don't exist anymore. We're going to have to futz around with this a little bit. I don't need an embedding anymore. Although I am curious, what do people do here? Generate text from each as no. Input shape, it's fine. I am curious what people do. Like, what kind of latent input do you use? How big a space do you want? And that's kind of up to you as far as how many, you just pick a number, and then that number dictates what your space is, and how wide of a variety can that be? Honestly, this can get pretty nuts. I don't know. We're outputting 32. We're outputting 32 times 28 things. Okay. So 896 things. So do we want 896 numbers, or do we want 512 numbers to help us not lose any information, given that this is all just fake data anyway. I kind of we'll give it 1024 numbers. They don't need to be in a particular shape, in fact, but I will just give it that many numbers, go nuts, have a good time. So, the first kind of layer is going to be convolution 1D, and that is a layer here, conv 1D, which I believe is a thing. It is, cool. I normally use convolution 2D if you're working on images, but 1D, they call it temporal convolution. You can always sort of rewrite an LSTM kind of structure, or an RNN structure is as though this kind of 1D convolution, as long as your sequences are sufficiently long. So I think that's fine. Filters. So how many things are we computing out? Over how long a window are we computing them? And then all this other stuff. Strides, valid. Padding, we'll see what we end up doing. Yeah, I'm not exactly sure how I want to handle that. But we'll see. Conv 1D. I should have left that open over there, because I'm going to need it open right So how many filters do I want to compute? I don't know, 32. That sounds. I like my models nice and small. People like 3 by 3, but I think I want a little bit more. I want 5 by 5. Well, it's not 5 by 5. It's just 5 long window. You know, over this window, like, what should the next character be? Hypothetically speaking. And strides is 1, and padding, I always like to use same. Yeah, so strides is 1, so how much do I move my windows around? I don't have any channels, but I do need some input shape information, right? Input shape. Pretty sure I need input shape information, because this is my first thing here. Input shape, is it over here? Is it really not? Input? Yeah, okay, input shape is what I need. Channels are last. So, we'll also need to encode this in a particular way. So what are we putting in? I just said I wanted, what did I just say? A 1024 long thing, right? 1024, comma. I think that's all I want. Like, so those are the channels. There's one channel. I think there's only one channel you can get away with without declaring that. Channel. One of channels first, channels last, channels first. What if I don't have any channels? For 100, how small goes for 128 length vectors with 6 time steps. 6 time steps, 128 length. Yeah, what if I just have 1? Can I be cheap and do that? Let's find out. Keras conv 1D. Oh, 1 channel. You know, single channel. Con 1D. This is exactly the input. That's not what I want. You might not be able to, in fact. Why don't we just make a dumb model and find out here? Let's find out with this. Hey. That is not working correctly. I have not added enough. There we go. Enough parentheses. Yeah, input 0 is incompatible with layer. Expected into dimensions 3, found into dimensions 2. This being the batch size, and that being, yeah, okay. So I have 1 channel input, I decided. So something like that can make sense, and then you can say model as summary. Get your thing going. Excellent, I'm already out of water. It's not even 6. It's dangerous. So at this point, you will generate 32 times 1024 things. So, you know, 2 to the 15 things for every single one of your data inputs. So I'm going to be generating that times, what did I say, 26180 times 4, of course. So now I'm consuming this many bytes, which is like 3.5 gigs. Just in the first layer here, keep in mind. Just in the first layer. So that's why this embedding space gets to be real important. Like, how much data are you using? Anyway, let's do that. And then we'll do model.add max pool. Is there like a max pool 1D? Hang on. That's what I'm not sure of. tf.keras.layers.max pool 1D. That's what we want. Cool. Max pool 1D. And so what is the pool size going to be? I think it should be 2, essentially. That's always what I think it should be. Yeah. You might want to muck around with this a little bit. We'll see. Because here we've gone from 1024 things to 32 times 1024 things, you know? 32 times 1024. What do you say? 32 times 1024. Which is far more things, you know? I've computed a lot of, 2 to the 15 more things than we really needed. So I'm wondering, do I really need that many channels of this? Like, maybe I can get by with, 8 or even 4. Because now I only have 8 times 1024. You think, what's the big deal? Well, I need to take this number, and now it's only going to be this big. Which is to say, less than a gig. Because I'm going to have more layers coming in, and it's going to be about this much for every layer. So that's going to limit what can fit in my video card, how fast is this going to be, can I shove all the data on there at once, things that you unfortunately have to think about. I think I just want that though. Let's do, how does this work exactly? Full size, strides, da 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 da. 2 will have the input. Default to full size, padding. I always like padding equal. Padding is going to be valid, but it's going to be 1024 long. So it's, we're always going to use powers of 2, so that shouldn't be a problem. But we will say padding equals valid is the default. Yeah, I'm not even worried about that. Not even going to worry about it. So that's one convolution. Now we'll do another convolution, but I want twice as many filters. I don't need this anymore. And the reason I want twice as many filters is because I cut my data size in 2 here, right? So in fact, let me make a new model here. Do this, right? You got this. You don't have any parameters, so it's not a very big model in terms of that. That's actually, oh, right, it's just 8 times 5 plus the bias terms. Then we'll do this max pool. Max pool one, I will define max pool first. In fact, let me grab this nonsense. Yep, and max pool 1D, there we go. Cool. Like that. And now, take a look at it. You know, it's the same, but now we've only got 512. So I got 512 things on 8 channels. So I only need half as many. I need twice as many filters if I want to like keep the same amount of information at that layer. Let's do this a couple times. We'll do a couple of these sort of little modules like this. Yeah. Each time I'll add more and more filters like this. So from 1024 down to 512s, from 512 down to 256. I say 256, but that's 64 right there. And then from 256 down to 128. You know, the goal being like, okay, I want to squish this down a little bit. Let's do the rest of these here. Okay, and then you do model.summary. And now, lo and behold, I've got 32 outputs right here. And so, what I could do at this point, I got 32 things with 128 channels each. What I really want is 32 things times, 28. That's kind of the thing that I want at the end. I want that many. I kind of want that many channels, don't I? But there's no way to make 28, unfortunately. It doesn't quite give me the. It's like I want something 32 wide, right, with 28 channels. So what I think we're going to do is do one more convolution. But we will output 28 things. And in this one, we'll have activation softmax. Oh, and I need to add an activation all around the rest of these. Let's just do ReLU. That's fine. Doink, 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 doink. Yeah, there we go. Otherwise, it was all linear, and that was kind of dumb. Do 2 linear things, it's the same as doing 1 linear thing. Now what does this look like? Now I have 32 things with 28 channels. And I should be the appropriate term, a input on that exact, I should get exactly each sort of feature here should sort of sum to 1 with this softmax nonsense. We should be able to just use categorical cross entropy. Let's find out. Should be able to. What if I predict? Hang on, does that work on one thing? Generates output predictions for the input samples. X batch size. Yeah. Okay, so let's do that. numpy.random.random. So just numbers between 0 and 1, because who cares? Of size equal to 1, 1024, 1. Let's see what happens here. Okay, that actually did a thing. And I want this to be my prediction, right? So this has the appropriate shape. We have put in one number. I have 32 channels, and each one has 28 values, representing the probability distribution. So if I say numpy.sum of pred along the axis equal to -1, the last axis, I should sum all these to 1. And I have not. Nearly so. Okay, but this is just some numerical instability. That's all this is. Because if you sum along the 32 axis, well, you get numbers that sum to more than 1 in every case. Because, of course, there's 32 things, and it's divided up the wrong way. So we can consider this a nice little probability distribution across the 28 letters that you're interested in. And what you're really hoping for is to see at the end a whole bunch of, what's the way I want to put this? A whole bunch of new lines. So the last character slot, I think, is what we want. Excuse me, over here, I guess. The last character slot. Yes, the last character slot. Over here. Obviously, these are all about the same because these are not trained on anything. So how would you actually train a model such as this? This is the generator. You might start training it by taking your input, by building like an autoencoder, so to speak. By creating this model, this is your output side. You have an input side that looks almost identical, but mirrored. And there you input the actual object, like using the one-hot whatever, your one-hot encodings of all your characters, and then use that to generate this. How many... Use that, you get to some input that's 1024 in the middle, and then you, from there, recreate your output. Alright, that's kind of cool. Model.summary, how many parameters are there in this? 72k, so about 2 to the 16. It's not a crazy amount. I will recall, however, that we only have, 26, 180. 180. We only have that many startup names, but we have a lot more characters, right? We have a lot of characters. What you're going to see is that the end will always be really strong towards this new line character. So what I think I want to do, this is build a model. I want to clarify that this is generator model, output side. What we can do, before we even do this GAN thing, is to do an autoencoder thing. And let me change all this word model here. Change model to output. Or generator, generator. Cool. So that's this thing. That's cool. And what I want now is to create an encoder. So let's make a new model. And what we want to do is mirror all of this stuff. So this encoder is going to take a one-hot set of our input data. So its original shape, let's keep model generator.summary, excuse me, generator.summary. Let's keep this round, because we're going to be working backwards now. Really, it's forwards, and this is backwards, but it doesn't really matter how you think about it. Encoder there, and what I want to do is add a convolution to this. Padding equals same, all this other nonsense. And the key part is the input shape. Input shape. Input shape. One of these days I'll get that right. And I'm going to put that on our line, so I don't go bonkers here. So, how are we going to get the correct input shape for our first convolution where we've got a 32 long thing, right? It's 32 long, and there's 28 objects, 28 parameters in each one. Those being the actual probabilities, but in our case, they're really the one-hot encoded pieces of data. So let's actually think for a second. I've got 26,180 times 32 times 28, times 4. Again, this is that 100 megabytes or whatever number. Not that big a deal. Because again, we don't have to make all these little subsequences. We don't need every subsequence. every contiguous subsequence. So that's fine. That should work just grand. I don't need 28 convolutions anymore. Instead, I probably want, like 128. So let's do that. Yes, 128. Here we're getting smaller and increasing the size. We're doing the opposite. Right. We're no longer going to be doing a conv1d exactly. We'll be doing a conv1d transpose, because we're going to be increasing the size, right? Conv1d. I mean, you could do the convolution and then you could upsample as well. There was a transpose. Is that only for 2D? That's interesting. There's a 2D transpose that lets you do this, because upsampling doesn't really have any weights. It just says like pick this method to upsample. Where it's like, well, I want to double the size, so like pick the nearest thing or interpolate or whatever it is that you're doing. Keras conv1d transpose. Is that not a thing? Issue. Yeah, what do you know? People have been asking about it. So it's part of TensorFlow, but it's not part of Keras, it seems. This is already implemented. In the branch file, we only have 2D transpose, not 1D transpose, but of course you can always pretend. Here's somebody made a layer to fake it. Someone made it. Should be available in TF nightly. Alright, so this is available a week ago. But not today. Well, that's a drag. Convolutional. I bet if we search transpose, that person is wrong. Transpose. Oh, hey, what do you know? Conv1d transpose. Oh, well, yeah. It's in this now. So I need convolutional, maybe? Convolutional, maybe? Come on. So I guess it's not in mine. What is the blame? I want to see you get blame. When did this happen? Is this really, a week ago or whatever? No, come on. Come on. This is nonsense. Transpose. Support 6 days ago, yeah. Really was 6 days ago. Huh, what do you know? All this nonsense. Oh my goodness. So unless I have the latest TensorFlow, I don't get conv1d transpose. That's a drag. This should have been done a while ago. Okay, but someone in here had a super fake. This is what I use. Okay, this is basically the same thing. Otherwise, we're gonna have to use a 2D transpose, but like reshape our data so there's only one, and it's gonna be a mess, and I don't want to do it. So we will use this code that someone was kind enough to put up, because the alternative is updating my TensorFlow, and that's always a headache. I don't want that. I want paste mode. That didn't work at all. Set paste. There we go. There we go. So conv1d transpose. In the latest TF, but not mine. Yep. I wonder if that's in like TensorFlow like 1.2.1 or whatever. That's actually a good question. Keras conv1d transpose 2.1. I meant to make a GAN for a 1D object. Hey, that's exactly what I'm doing. It will consume a lot of time. Interesting. Is only a convolutional layer with upstate? I don't think there's a division of convolutional layer. Yeah, I mean, you can always upsample and do a convolution. It's not really a big deal. I'd rather just do the transpose directly. So we will just grab this and use this. And hopefully this is fine. If it's not, so auto indents, turn that off every time. Every time it gets me. Okay, there we go. So now I should be able to do conv1d transpose, which kernel size, strides, padding valid. Again, this should expand it. This should double the size. Ought to double the size. Now I'm curious. I don't want to call it generator. I want to call it encoder. Let's see what happens here. Conv1d. It helps if I can spell. That's always a good, important thing to do. Input shape. Oh. Oh. That's not good. So what we need to do is like make a proper input. tf.layers, tf.chars.layers. Input, I think, layer. Used to instantiate a chars tensor. It's either input or input layer. Or input shape. Like, which one of these would I want to use? Layer to be used as entry point in network, a graph of layers. Either wrap an existing tensor or create a placeholder tensor with input shape. I think that's what I want. Input shape, and this is where I'm going to put this stuff. Grab this. Put it right there. Take this. Come on back now. There we go. Okay. Close that off. Now let's see if this works. Also, I'm going to need input shape, which don't have right now. Input shape. There we go. Cannot, not input shape, input layer. Again, spelling. That's one of my colleagues. He writes excellent code, but his spelling is subpar. That's again, that's the thing that grinds me most about him. He's doing all right. He's doing pretty well. Okay. Encoder.shape summary. Let's take a look. Make sure we got the thing we expect to have. Yes. Okay. Now we can do a conv1d transpose with an output shape of 32. No, actually, I wanted the shape to change. I want the shape to be 64 doodads, right? Yeah. This is wrong. Does conv1d transpose not do what I thought it did? What does tf.squeeze do? tf.con2d. Oh, he just does the con2d transpose. Keras. Oh, in fact, he's literally using the con2d transpose. I mean, he gets the job done. 2d transpose. Sometimes called deconvolution. Oh, it's the same thing, isn't it? I could have sworn. Desire to use transformations going in the opposite direction of normal convolution, something that has the shape of the output of some convolution, something the shape of the input, while retaining connectivity pattern with that is compatible with that convolution. Kernel size, strides, output padding, I don't really care about any of this nonsense. Huh. Yeah, I could have sworn. I could have sworn that was supposed to give me a different output size. Clearly, however, it did not. Yeah, I expected to like double my size here. Harumph. Output shape. Batch filters, new rows, new cols. Input shape, rows, cols. So where's new rows, new cols to figure it out? New rows. Nowhere. Wasn't that cute? Here's the first layer model for the keyword argument input shape. That's annoying. Strides. Let's see stride not equal 1 is incompatible specified iteration rate. I don't need an iteration rate. Data format, dilation, activation. kernel. All right, now I need to do some research on this. Of Keras conv 2D transpose, like increase size. I could have sworn that's what I was doing. Yes, you can always upsample. That's the obvious thing to do. Upsampling, upsampling, upsampling. That's no weights again, no weights. Just does an upsample based on whatever heuristic you want to use. The generator, no, get me to the conv2D transpose. Put his notes that kernel defines convolution, what a direct convolution is determined by how the forward and backward passages are computed, sure, whatever. You want an output that looks like this. Yeah. Again. 1, 1, 1, 2, 2. So I snark around with my strides. Use one filter, but 1 by 1 kernel, and a stride of 2 by 2, so the 2 would use upsample. Okay, so that was my problem. I didn't fool around, I didn't fix my strides. I think 2 by 2 is what we want. Well, 2 by 1 rather. So what in my conv 1D transpose? Do I have a strides argument? I do. Okay. Strides equals 2. I believe that will do what I want. All right, let's try this. Encoder.summary. Yes, now we have 64 things. That's what I want. Twice as many. Okay, that'll work fine then. You do that silliness, and this sort of combines the convolution and the max pooling. Like you invert the max pooling after a fashion. So we do want some activation though. We don't want just linear stuff. So let me put this here. Let me say activation equals rel u is fine. It's always fine. Rel u, always fine. And by always fine, I mean like it's not, but it'll get the job done right now. Activation was an option? No! What? I have to put activation on afterwards or before or some other thing? Well, I'm gonna fix that. I'm gonna fix that right now. Because if I said tf dot keras dot layers dot conv 2D transpose, you take activation default none. Where are you? Where is it? Activation. Activation equals none. Yes. Okay. Cool. Actually, what I want to do is just star keyword args. That's all I want. And then, no, I don't want to do that. We're making this layer, and then, okay, yeah. Nope, oh jeez. Oh jeez. Let's come here. There we go. And then keyword args. Star keyword args. I don't remember how to use this silly argument. Star keyword args, right. I think you can pass it in this way. I don't actually use that all that much. Python star keyword args. Yes. What's the... This gives you a list of whatever things are. Keyword args gives you a dictionary. I think you can just pass that to it. I'm pretty sure. Pass, hang on. Keyword args. To function Python. Yeah, can I just do that? Is that just a thing I can just do? Is Python that convenient? That I can pass star keyword args to something? Or all these examples just about reading star keyword args? Here we go. Yeah, okay, you can do it. Right, this is a dereference thing. This is in a little bit of a strange way that I don't often deal with. This creates your layer. This just says pass in all this stuff, so I don't have to think about it. Yeah, that's super good. Let's do that. Perfect. And then I can just pass in activation rel u, and I shouldn't have to. Yeah, perfect. Coder.summary. We have 5 minutes left, but we are very close, because now I can just take this, take these two. Well, tell you what. Let me actually put this on one line, just so I can go bang. Okay, what did I say the sizes were? 128, 64, 32, 16, and then there was 8 was the last one, and then to 8. And then we'll see what we got here. So we got those already. Let me add these and see where we end up. Okay, I have 1024 things that are. I have 8 things defined on 1024 objects. So what I want to do actually is in this final one, don't change the size and just give me 1 object. And then I have 1024 things right there with 1 channel, which conveniently is exactly what we want as input here. Okay, we're not going to get to actually properly training the model right now, but this is going to be a cool thing. Now we can do encoder like decoder. You could think this is a decoder as well, but we'll call it a generator. What I'm going to do is make a capital M. We'll just make a model. Model equals sequential, right? And I'm going to say model.add of encoder. I'm going to say model.add of generator. And then we'll say this stuff. Except now it's model.compile. See if we can do this. I think we can. Ho ho. Ho 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 ho. Look at that. Now we say model.summary. Go. Model has not yet been built. That's a lie. Oh, I guess it. No. Oh, because I never built this. Excuse me. Yeah. Calling build or fit or specifying input shape the first layer. Except, I mean, we kind of did specify an input shape, right? I mean, we did. Really, we did. Really, yeah, we really did. Can encoder take an input shape? Yeah, inputs, yeah. When you add, can you specify a shape there? No, you cannot. Tell you what, let's just do model add input layer. We'll just do this exact same thing here. We'll change this to model. It's the same thing. It's not going to do anything to it. It's all still good. See if that works now. Yeah, okay, there we go. Note that it just reads that as a, this is the whole model. This is the whole model. There's nothing too goofy about it. Okay, if you wanted to train this then, what does my data look like? Oh boy. Let us, we have 1.5 minutes. This is probably a good place to stop, actually. Okay, so what do we have now? We have changed entirely over to a 1D convolutional model to predict 32 probability vectors. Each one of those vectors is the probability distribution for a particular letter in that position, given some inputs. We have a generator half right here that will do, given some kind of latent space input, this 1024 numbers will generate some output. How do you get those 1024 numbers? A couple different ways. One, you could generate what's called an autoencoder, is what we have here, this encoder, which takes in the actual input, does a bunch of stuff to it, and then spits back out your answer. And now that I think about it, this actually should be less, smaller in size than this whole thing. Huh. Hey, you know what? Yeah, I'll make this like 256 actually. That yeah, that should actually be smaller. Yeah, this might need futzing around with a little bit. Might need to be careful about how we're doing this. Because that's 1024. Yeah. We'll leave this be for now. I'll leave it be for now. We might want that to be smaller so it forces some sort of compression when you try to do the encoder. That's not actually that big a deal, though. Otherwise, the model can literally just save all the information it needs into this 1024 long vector and then like unpack it through this series of convolutions. Usually that doesn't happen because the network's not that smart, but that's something that can occur. Okay, so we've got this encoder decoder thing going on. Next week we want to train this up a little bit actually, just to make sure this works. This does some things we expect, but then we will change it up and we will make a discriminator, and now then we'll train our generator with our generator and the discriminator. The discriminator gets trained on the actual data and gets trained on real data and gets trained on the output of the generator. The generator only gets trained based on how the discriminator does. You could, however, like train the generator first with the encoder just to get something that's vaguely reasonable as a starting point, like a little bit of pre-training, and then go back and fix it. And we might do that. Okay, that is all I have for tonight. Thank you all very much for watching, and don't forget, stay safe in the data mines.